What is principal component analysis in AI and machine learning? So, artificial and machine learning are transformed many industries by enabling data-driven decisions, predictive analysis, automation. A significant challenge in AI and machine learning is just dealing with large data sets that may contain thousands or even millions of features. So high dimensional data can result in increased computational cost, overfitting, challenges in model interpretability. So PCA is a widely dimensional reduction technique that addresses these issues by identifying, preserving the most critical information in the data. And PCA is a fundamental in the fields of AI and machine learning, especially in pre-processing, exploratory data analysis, feature engineering, by projecting high dimensional data into low dimensional subspace. So it simplifies data analysis, improves performance, and facilitates visualization. So we're going to explore the theory, implementations, um, applications, advantages, limitations of PCA and AI and machine learning. So we will be providing the overview of role in modern data-driven um systems. If we talk about fundamentals, what is PCA? So it's a statistical method that transforms high dimensional data into low dimensional form while retaining as much as one of the variability in the original data as possible. So it was developed by Carl Pearson in 1901, later formalized by Harold Portley. So PTA aims to identify patterns in data and express them in terms of set of orthogonal component. The key idea behind PCA is to find new coordinate system where the axes correspond to the directions of maximum variance. So the new axes are known as principal components, and each subsequent component captures less variance than the previous one. So by projecting the data onto these components, PCA reduces the number of features, eliminating redundant and less informative dimensions. And if we talk about mathematical background, so PCA relies on linear algebra concepts, particularly eigenvectors, eigenvalues to transform the data. So given a set X with n samples and d features, so these steps are to perform PCA, like center the data, compute the covariance matrix, calculate the eigenvectors, eigenvalues, and sort and select principal components, which is the which is like ranking the eigenvectors based on their corresponding eigenvalues in descending order and select the top k components. And then is projecting the data, which is transforming the original data using selected eigenvectors. So yeah. So if we talk about theoretical insights, so first is uh, geometric interpretations, and then is like variance maximization, dimensionality reduction, and relation to the single decomposition. So if we talk about implementing the PCA, which is PCA algorithm, in which we standardize the data. Basically, we scale the data to have zero mean and unit variance, and then we compute the covariance matrix where we calculate the pairwise covariance between the features, and then we perform the eigen decomposition where we find the eigenvalues and eigenvectors of the covariance matrix, and then we sort and select the components. So we choose the top k eigenvectors based on their eigenvalues, And in the last, we project the data where we transform the original data using the selected component. And so if then is like Python, the another we can do is like Python implementation. So PC can be easily implemented using popular libraries like NumPy, scikit. Uh, so these are the method. And if we talk about application of PCA and AI and machine learning, we start with the data pre-processing and noise reduction, um, which is high dimensional data, normally contains noise, missing values, irrelevant features that degrade the model performance. So PC helps in filtering out noise by focusing the most significant components, effectively denoising the dataset. So for example, in image processing, PCA can be used to compress or and reconstruct images while removing noise and preserving essential features. Similarly, in natural language processing, NLP, PC can reduce the dimensionality of the word and embeddings or term document matrices and improving the computational efficiency. And if we talk about feature selection and engineering, so PCA is widely used in feature engineering to create new features that capture important patterns in the data. The principal components themselves can serve as a new feature, reducing the need of manual feature selection. Moreover, PC can identify and eliminate multi-collinearity among features. In regression models, correlated feature can lead to unstable coefficient, estimates, and poor generalization. So by projecting the data into orthogonal space, PCA removes linear dependencies and improves model robustness. And then the third is visualization of high dimensional data. So visualization is a crucial step in exploratory data analysis. So it becomes challenging when dealing with high dimensional dataset. So PC addresses these issues by projecting data onto two or three dimensions, making it easier to visualize clusters, patterns, outliers. For example, clustering in clustering problems, PCA is often applied before using algorithm like k-means, hierarchical clustering to visualize the grouping in the data. Similarly, in classification problems, PC can reveal class separability and guide the model selection. And then is uh, advantages and limitations. So if we talk about advantages, dimensionality reduction is one of the advantage where PCA reduces the complexity of the high dimensional data, making it easier to analyze and model. Then is noise reduction. By focusing on component with high variance, PCA filters out noise, irrelevant information, computational efficiency, where the reduced dimension lead to faster training, interference times for ML models. Then is visualization. So PCA enables the visualization of high dimensional data in 2D or 3D, aiding in pattern recognition and hypothesis generation. And in the last is featured decorrelation, which is the orthogonal components produced by PCA, which eliminates the multi-co-linearity and which enhance the model's interpretability. And then if we talk about the limitations, first is linear assumption. So PC assumes linear relationships among features and may not capture non-linear patterns. And then is loss of interpretability. The transformed features principal components may lack meaningful interpretations. Then is sensitivity to scaling. So PCA is sensitivity to scaling features requiring careful pre-processing. Then is variance-based selections. PCA relies on variance as a criterion, which may not always correspond to the most informative features. and then potential over simplification, which is the reducing dimensions too aggressively that can lead to information loss or reduced model performance. And if we take the case study like applications, so uh, like image compressions and face recognition. In image compression, PCA used to reduce the dimensionality of images by representing them with fewer components. For example, Egan faces method in face recognition relies on PCA to identify most important features, distinguishing faces by projecting new images onto these components that enables efficient face identification. Then is stock market analysis can be done, and so PCA is employed in financial modeling to analyze and predict stock prices by reducing the dimensionality of market indicators. By identifying the principal components, analysts can focus on the factors that drive the most variance, such as market trend or economic indicators. Then is healthcare and genomics, uh, uh, where PCA is used to analyze gene expression data, identify patterns related to diseases, genetic variations. So, by reducing these dimensionality of high through throughput sequencing data, researchers can uncover meaningful biological insights and develop diagnostic tools. So, in conclusion, PCA plays a vital role in AI and machine learning. So, addressing the challenges posed by high dimensional data, its ability to reduce the dimensionality, which improves the computational efficiency and facilitate the data visualization, make it fundamental tool in data pre-processing and analysis. While PCA has some limitation, its extensions such as kernel PCA, sparse PCA provide solution to complex scenarios. So as the data continues to grow in volume and complexity, the importance of dimensionality reduction techniques like PCA will only increase. So by understanding and applying PCA effectively, data scientist or AI practitioner can unlock the full potential of their data and driving advancement in various domains. Thank you for watching. Please like, subscribe,